This is IAQ Radio, Indoor Air Quality Radio, the voice of the indoor air quality industry, with your hosts, Radio Joe Hughes and the Z-Man, Cliff Zlotnick. And now, Radio Joe Hughes.
Good day and welcome to IAQ Radio Plus. It's episode 741. This week we welcome Dr. William Chapman. We're going to talk about chemical monitoring for indoor air quality and odors. Before we get started, let's thank our sponsors. They're the reason we can continue doing the show. IAQ Radio Association sponsors are AIHA, the American Industrial Hygiene Association at AIHA.org. IICRC, the Institute for Inspection, Cleaning, and Restoration Certification at IICRC.org. The Restoration Industry Association, RIA, at restorationindustry.org. The Environmental Information Association, EIA, at EIA-USA.org. Actionable Insights at getinsights.org. IAQ Radio industry sponsors are Particles Plus at particlesplus.com. BioPlanet at byoplanet.com.
And now you can win a cool prize. It's time for the IAQ Radio trivia question. Be the first to correctly answer. Simply email your answer to czlotnick at cs.com. Or if listening live, just text your answer from your computer. And now, here's the Z-Man.
Hello, everyone. Congratulations go out to John Lapotere, IAQ Solutions, Sanford, Florida, who was first to identify Reverend Woody Leach and Emily Stewart as the two concerned citizens who founded Community Housing Partners in 1975. Here's today's IAQ Radio trivia question. To whom is the invention of modern gas chromatography attributed to? Back to you, Joe.
All right, today's guest is Dr. William Chapman. Air by CC² was founded by Dr. Chapman in response to his experience working in the air testing industry. He wanted to provide proven solutions to indoor air quality problems. He has a PhD in chemistry from Penn State and completed his postdoctoral studies at Columbia University. Welcome to the show, Dr. Chapman.
Hey, well, thanks a lot for having me. I really appreciate it.
It's great to see you. Great to meet you. And by the way, I didn't mention you're in Boca Raton, Florida. And do you go by Air by CC² or ABC? How do we say that?
Well, ABC sounds great to me.
All right.
We're trying to keep things simple for our customers. So
a little bit easier for me too. All right, Cliff, why don't you go ahead and start things off today?
Sure. Thank you. Okay. When Joe and I have done in our careers significant amounts of indoor quality consulting after problems, and a lot of times we would tell the client, your problem most likely is going to be found in one of three areas. It could be biological, it could be chemical, it could be particulate. And I'm wondering, with your knowledge and experience in the laboratory and everything, is there anything else we should be looking for besides those three things that should be added to the list?
well, I think that your definitions are very complete. The one thing I might add, just for the sake of adding something, is nanoparticles. When we talk about particulates, we're usually referring to things that we can catch in a filter. And the filters are usually 0.45 micron, mixed cellulose ester filter, from SKC. That's a typical dust filter. That's going to catch your particulates, PM 2.5 and so on. But how about particles that are smaller than that, but are larger than molecules, larger than, say, a polycyclic aromatic, pyrene or something like that, or larger than formaldehyde, certainly. And these would be things like carbon nanotubes or the buckyballs that we see in the laboratory. Those are like the ideal forms of these nanoparticles. But in real life, in a fire situation or just any indoor air situation, the nanoparticles would be less ideal. It's not going to be a perfect carbon nanotube floating in the air. It just doesn't happen. I think that's an area that's going to be really interesting in the future, because the nanoparticles can be quite different from larger particles.
One of the things that I guess we've heard from other guests is that sometimes the use of certain equipment inside of homes, such as ozone machines and hydroxyls, have been known to create nanoparticles. So it's good that they be added to the list.
Yeah,
Joe?
those are interesting points, and it's just a new area for study. It's kind of stuff you might detect, using infrared device or Raman, or a mixture of infrared and Raman. But labs today aren't seeing such things. We're not going to see it with our GCMS systems or HPLCs. You're not going to see it in a dust analysis because you're not going to catch it on a 0.45 micron filter. So then it's sort of a gray area. Something I always thought was interesting about nanoparticles is that their properties can be really different from larger particles. So gold particles. I've worked with gold nanoparticles. Most laboratory folks have, and 100 nanometer gold particle, 150 nanometer gold particle looks gold. You have a solution of them in water or slurry, and you look at it, it's golden in color. Now let's compare that to a particle that's 20 nanometers in diameter. That turns purple. It's very intense purple. So it's such a radical difference. And I must wonder how size affects things like smell.
Yeah.
These are things we don't know. So gotta wonder.
Let's introduce you a little more to our audience. You're currently running your own lab in Boca Raton, but prior to that, give us a little background. You went to Penn State, got your doctorate in chemistry there.
Yeah.
Did some postdoctoral work at Columbia. What kind of work did you do after that?
Yeah, so I moved to the San Francisco Bay Area, and I basically worked in the medical device biotech area in analytical chemistry for a good 20 years. So my first job was at the old Siva Corporation after they were purchased by Behring Diagnostics and Roche and so on. And we developed some new methods for detecting infectious diseases, which it was quite the interesting project. At the time, the Roche had purchased patent rights to the polymerase chain reaction. It was invented by CC² Corporation in Emeryville, California, and a very powerful technique. And we can talk later on about using that method to detect mold in people's houses. That's the newest and coolest, and it really works. But I was working for Behring Diagnostics, Siva Corporation. They wanted to have their own method, so we're working on finding ways around patents, basically, and develop some really cool DNA detection techniques. And they were purchased again and sold and so on. So that's business. And I worked for Hitachi, gained appreciation for Japanese hardware and equipment, and worked for CC² Corporation, where we developed methods for measuring cholesterol. Those are probably the most successful products I've worked on and developed. And of course, the company was sold again. But those are sold by Abbott now. Abbott Laboratories ended up with the ownership of the CC² products, and they're used in the CVS Minute clinics now to measure cholesterol for lipid profiles and some other tests for liver enzymes. So.
And how long has ABC been in existence?
We've been here since about 2021. So when I started the company. Yeah, before I worked here, I worked for Advanced Chemical Sensors, which was one of the original air testing companies. You probably heard of the Advanced Chemical Sensors products. And that company was founded by Larry Locker in the 80s. It's the original diffusive air sampler company. And so I worked there for 5 years after Larry retired. I was a laboratory director there.
And how did you get interested in odors?
Odors? Oh,
yeah.
Well, tell you what, at Advanced Chemical Sensors, odors were a super big challenge because the original air testing products did not have the sensitivity to detect odors. So it'd have a customer complaining after a fumigation of some severe irritant in their house, and we go and measure and look for chloropicrin, which is the indicator gas for most fumigant work today. And we detect nothing, and we can talk about why that is. But, it's a challenge to detect an odor in someone's home with, the classic technologies. It never really worked. The nose is incredibly sensitive. And, jamosin is one of the most common scent chemicals made by molds. Black mold's going to make jamosin, and Aspergillus niger makes some jamosin, and that's the classic mold smell. And the nose can detect that stuff down to parts per trillion levels. So until very recently, we haven't been able to measure chemicals at those sensitivities in air. And now we can. Jamosin still challenges us because that's probably one of the lowest odor threshold chemicals that I know of. Nose is incredibly sensitive to that. But yeah, it's an interest in odors is more the challenge, and the technology is there to detect them. It's just a matter of doing it in many cases, and that's sort of what our company's about, is bringing some newer technologies to market. We have our GC mass spec system, which is new and updated and unique and capable of measuring a lot of odor compounds. So we can measure chlorpicrin in people's houses now. And, that's the indicator gas using during fumigation. And, we've detected, I actually detected in a chamber test in a man's shorts. The shorts became known as hot pants, that they were present in a dresser during fumigation. And, the fumigation company followed the EPA protocols, which involves adding chlorpicrin, which is the tear gas, war gas used in World War One. And EPA has fumigation people adding this to their fumigation gases, so as an indicator for safety. The trouble is the stuff sticks around. It soaks into certain types of fabrics. This is Volcom shorts, really nice pair of shorts. And the owner of the house said, a month later, I can't wear these shorts. It's driving me nuts. So we put them in a chamber and tested, and yeah, there it is. We're we're seeing chlorpicrin now. So our new methods do allow us to see things like that.
What drove him nuts? Did he have itching or
burning?
Interesting.
Yeah, like a burning sensation.
Cliff, let me turn it over to you.
Yeah, sure. One of the things that I noticed is that you prefer a different sampling strategy and method that's utilized by other analytical laboratories. And I was wondering if you can tell our audience a little bit about what you're recommending and why you're recommending it.
Our sampling strategies? Well, we usually use diffusive samplers for most projects. And the tradition is to use the air sampling pump. And there's some history behind that. Why is that? Why do you want to use an air sampling pump? Well, the air sampling pump allows you to know exactly how much air you've tested. And then the laboratory can take your sampler, which contains the absorbent. We can measure the mass of the chemical we want to measure in that absorbent. And then you can calculate a concentration. And if you're working in an industrial hygiene environment, where you need to provide a number that's very accurate for comparison to, say, a government standard, well, then you need to have a really good understanding of the error, and you have to have basically a validated, calibratable volume measurement, and that's what that pump provides. So that's why people use pumps in industrial hygiene environments. We analyze sampling tubes when you need that type of accuracy. But what we found over the years, especially when it's advanced chemical sensors, is that we compare diffusive air samplers, which is the air sampling badge, to the tube in a chamber test. We get really similar results. In fact, in one experiment, we didn't do the experiment. We worked in collaboration with a German laboratory called the IFA, and that it's it's a laboratory in Germany that generates standard vapor concentrations for validation of industrial hygiene tests for laboratories like ours. So they send us samplers typically. We analyze them. We send the data back, and they tell us if we're correct or not. We participate in a lot of programs like that. But the IFA has a standard vapor system set up. So what we did was we had them sample with sampling tubes. And at the same time, we had our badges, our air samplers in the same chamber. And they have a device set up so that they can move an air sampler at a known rate in a chamber, as if it's attached to a person walking around a room. And so we compared the results from the air samplers and the diffusive air samplers, the badges and the tubes. We got basically the same results within the same era. So I think diffusive samplers are ready for prime time, and we could do good measurements with them. The challenge is measuring the rate at which chemicals diffuse into the sampler, and it just takes time and effort. And it's something that we can do here, and we do.
Well, there would seem to be some advantages to utilizing them.
Yeah.
I would think. And what might some of the advantages be?
Well, sure. There are a lot of advantages using diffusive samplers. One, you don't need a pump. You don't need to pay for the pump, but you have to worry about the battery running out. Two, you can sample for a very long period of time. You can sample for 24 to 48 hours or even longer with some of our newer adsorbents. And that allows you to get a better average sample and allows you to see clouds of chemicals that may be appearing in an indoor air environment that are not always there, or at least not always at a high concentration. And so, for example, in a Florida home during the day, the air conditioners run continuously. The air's being circulated, and maybe what you're measuring is being diluted by that flow. At night, the air conditioner turns off. Well, then maybe you start detecting something in the kitchen then with your sampler. You wouldn't see that with a sampling tube. And we do see things like that with diffusive samplers all the time. So diffusive samplers are also nice that you can put them on a string and drop them down inside a wall. You can toss them across the attic on a string, so like a mouse trap almost. If you ever use mouse traps in your attic, and you can put them in places where the rats go that you can't, well, you attach your string and sort of toss it over there, and same deal. So yeah, they have those types of advantages.
And do you ever have people wear them?
Sure, people can wear them. They're in the workplace environment. They're typically worn. So we sell an air sampler for measuring the anesthetic gas isoflurane that's used in veterinary hospitals. That's one of our more important products. And those are worn by the veterinary technicians and the vets when they're working with an animal with this gas. It takes an hour or two for them to complete the procedure. And there's one on the collar, and it measures their breathing zone. And we'll have different vets and different technicians wearing the same sampler for the same procedure, and you get different numbers, and you can learn from that. One of them took the animal from the operating room into the recovery room. The other one went off and did something else, and the person who took it to recovery turned out to have a really high concentration. So now you know when they're being exposed. So you can learn a lot from the diffusive samplers.
Interesting. Cliff?
Yeah, let's discuss a case study. Let's talk a little bit about post-ozone reactions. I understand, and go through that with our audience, if you wouldn't mind.
Well, sure. That sounds great. Yeah, we have a brief presentation for that. And of course, homes here in Florida, around the country, are having more problems than ever with mold intrusion. Due to changes in climate and increases in the ocean level. The insurance company in Florida are declaring bankruptcy and having all sorts of problems due to increased numbers of claims. So the question then is, what do you do about that? Number one problem in flooding is mold. Water comes in, everything gets wet, and the mold starts growing. So this is terrible. And so I think it's something people have a lot to learn about. And we're in the lab here. We're not out there doing the actual remediation. So what I think is most important that would come out of this meeting, this presentation, is that maybe we start talking more to people who do the remediation work, and have more interaction going back and forth, so we can improve methods. And there's going to be a lot of businesses in there in the future, and but we have to be able to solve the problems. And that means, the mold remediator has to remove the mold from the house and satisfy the customer and leave the house in a condition where the customers can live in it. And the trouble in this case study, and the problem with a lot of people now, is that when the mold remediation process harms the indoor air quality of the house. And so in this case, it's the house that's in Plantation, Florida. It's a beautiful house that's on a lake. There's a lake out back. They have a porch out back, a really nice view. And this house had a mold problem. What they had was water intrusion occurring through a crack in a wall that was on the left-hand side of the house on the first story, right near the foundations. And a crack formed between the block and the foundation, and water from the neighbor's sprinkler system went into their house, and they ended up with mold growing behind their bed in this bedroom. So they called the mold remediation people, who removed the mold, removed the wall, put in, cleaned the slab, removed the floors, of course, and put it all back together again. It looked great. They did great work. The work was done in 2020. Now, the owners came back to the house and became very ill because of the quality of the air and had to leave the house. So they rented a condo down the street, lived down the street for a year. And about that time, they found me and some other people I know in the area. Maurice from Environmental Research was involved with this as well, Maurice Baum. So could you give me the next slide? Do I have control of the slides?
Grayson, give us the next slide. There we go.
There. So before I got there, the mold people had run some VOC tests. And according to these VOC tests, the air quality was very good in the house. And these are the results: ethanol, limonene, acetone, and hexanol, which is very typical of these houses. I think hexanol is actually a clue, but at the time, this doesn't explain the indoor air quality. Hexanol is a clue, though. So next slide, please. So I know from personal experience working in chemistry labs that ozone is chemically reactive toward chemicals called alkenes, carbon-carbon double bonds. And ozone reacts with carbon-carbon double bonds, producing an ozonide. And ozonides break down to give aldehydes. So since the place is ozonized, we want to give it an aldehyde test. So we did an aldehyde test. This was during COVID, and this is before I had the laboratory here. So this was done with the old analytics lab in Ashland, Virginia. And what we found was elevated formaldehyde. Yeah, it is at 46.8 ppb, which is an elevated level. That's a pretty irritating level. It's borderline. The owners of the house are retired in their 70s, and this concentration is annoying to people that general age group. So I thought, well, okay, formaldehyde must be a problem here. Now, so could I have the next slide? Now, where would formaldehyde come from? I was describing the reaction. So we know ozone reacts with alkenes to produce aldehydes. And so here we have the chemical structure of unnatural rubber. This is a simplistic version of unnatural rubber. It's usually a copolymer, so there's some acrylonitrile or something else in there too. But this is just poly 1,3-butadiene. It has 1,4 and 1,2 repeat units. And the point here is that the 1,2 repeat unit is going to react to ozone to give this ozonide. That's 3 oxygens. And then this is going to lose an oxygen atom to give aldehydes. There's an aldehyde attached to the polymer, and then there's a second aldehyde, which is formaldehyde, which goes floating away. So, this is the rubberized coating on the back of the bathroom rug or any area rug. In Florida, we have a lot of area erosions. We have tile floors for safety. One thing to notice from this slide is that the first step, the reaction with ozone, is really fast. And that doesn't take time at all. It takes a few minutes. Now, the loss of oxygen, though, is not so fast. And this is not obvious. The oxygen doesn't just disappear. The oxygen has to go somewhere. There has to be an oxygen-getting molecule involved. So in the lab, if you were to do synthesis, a good oxygen-getting molecule is dimethyl sulfide. It would react with the ozonide to give a dimethyl sulfoxide. That's very common. I've done that a lot in synthesis. Because you use a phosphine, we get the oxygen to give a phosphine oxide. Obviously, we don't have dimethyl sulfide in our houses, at least not unless you have a really bad mold infection. And we don't have phosphine. So then where's this oxygen going? Well, I can't exactly say, but I know that this formaldehyde is coming out over the period of months and years from these ozonized houses. And so we have a low level of an oxygen getter that I think is regulating this rate. And that oxygen getter, I think, is nitric oxide, NO, which, it's produced by people. We make nitric oxide. We have nitric oxide synthase in the inside of our arteries. It makes nitric oxide, which acts as a vasodilator. If you're a bodybuilder, you know about NO. And so the NO reacts with this oxygen to give NO2. And oh, excuse me. No. Okay, sorry, excuse me, sorry. I'm constantly being interrupted here by people trying to deliver food. So anyway, my point though is that the oxygen from the ozonide goes to nitric oxide to give nitrogen dioxide, and that's where the formaldehyde comes from, and that requires the presence of people who make the nitric oxide, NO. So could we have the next slide? So now while we were analyzing this data, I asked analytics to send the sample off to these folks at the Shimatsu Center at University of Texas, Austin, who I know. And we've been talking about looking at these samples using an LC mass spec method. It's called ESI TOF mass spec. It's sort of the newest and coolest in the analytical methods, and these guys are showing it off. Shimatsu gives them a free machine, and they can show everybody what they can do with it. And what we found in that sample was evidence of the presence of malondialdehyde, which is a structure drawn down here. It's 3 carbon atoms and 4 hydrogen, 2 oxygens. It's like a mini glutaraldehyde. And this is a chemical that comes up an awful lot in medicine. And could I have the next slide? Yeah, so it's becoming a more popular topic. And the reason I was interested in it to start with is because, when I was at Cholestech, we were interested in coming up with better ways of diagnosing cardiovascular disease. And, everyone measures LDL, low density lipoprotein now. That's our marker of atherosclerosis development. Well, why would that be? LDL is sort of part of your body. Why would it create problems? Well, the idea then has come from others in the medical community is that the LDL becomes damaged somehow. It's oxidized or damaged. And then the damaged LDL is what forms plaques in your arteries. So how is it damaged? Well, number one cause of damage is MDA, malondialdehyde, which comes from the oxidation of vegetable fats. These are 1,4-diene containing vegetable fats, so the polyunsaturated, omega-3s and omega-6s that we need to eat that are healthy. Now it's taken a long time for people to really understand this, and that's because it's difficult to study MDA because you can't buy a bottle of MDA. It's an unstable chemical. It polymerizes really fast, and it gives a sort of nondescript polymer product that doesn't just depolymerize like formaldehyde. Formaldehyde is an aldehyde that forms polymers. Yeah, that's why you can't just capture formaldehyde and analyze it directly. that forms polymethylene oxide. But if you heat that up, formaldehyde comes back out again. So the MDA is not that way. So that makes studying it very difficult. And for years, people tried studying it using what's called the T-bars assay in blood. But that didn't go very well because you need calibrators, and there's no pure MDA. So people had these approximate calibrators they were using, which didn't work very well. So, but this is something that's being ironed out now. And very, very recently, Aldrich Chemical Company has been offering a new form of MDA, which is an enolate of it that's stable. So we can actually calibrate machines now. So now we're seeing a real uptick in the study of MDA in the literature, especially in medical blood tests. But we don't see any tests in air. So what's going on here? So next slide, please. Yeah, so malondialdehyde, as I said, it's not a stable chemical that you can just buy. Now, if it's produced on a surface due to ozone oxidation, then it's going to evaporate just like water. Its boiling point is estimated to be about 108, so it's published. That's a calculated number. But I think, it's in the ballpark of toluene. So it's a pretty volatile small molecule. Now it's stable as an enolate in the lab. So Aldrich's the brilliant work that's made it available now is that it's available as a tetrabutylammonium salt. So this is an enolate form, so it's stable as a salt. And dissolve that in water in a little carbonate. It lasts for months. So now the native stuff is evaporating from a surface that's an indoor air contaminant. It's going to have a pK of about 4.5. So it's just like acetic acid. So what that means is you can capture it with base, like carbonate or TEA, triethanolamine. Yeah. So next slide, please. So we developed a method for measuring this in indoor air. It's one of my current interests, working on this slowly when I have a chance. And as I said, we can capture triethanolamine, and they're commercial samplers that contain triethanolamine, like a nitrogen dioxide sampler from SKC, commercial sampler. So we could just use that one. Or you can use a bubbler with carbonate in it, or again, you can use SKC paper that contains sodium carbonate. And so far, we've tested and validated two methods for detecting it in air samples. One's ion chromatography, and the other is the medical test, the T-bars test that's used in blood testing. That works great. T-bars just reacts with malondialdehyde to produce a red color, so you detect it using absorbance spectroscopy. It's a colorimetric test. So next slide, please. So we detect malondialdehyde. Well, why would it be there to start with? What is going on here? Well, let's take a look at the chemistry of alkenes that we find in the home. And I think I already showed you the structure of unnatural rubber. And natural rubber has double bonds in it, so those will react to the ozone. Well, what else? Well, we have vegetable oils in the house, especially in the kitchen. And the kitchen is going to be coated with a thin layer of vegetable oil, olive oils or some type of oils. And they all contain, the vegetable oils contain a lot of unsaturation. They contain carbon-carbon double bonds. We have monounsaturated fats, as they're called, like oleic acid, and we have linoleic acid as an example of a polyunsaturated fat. And on the left-hand side of the slides, the acyl triglyceride molecule, which is the oil, that's vegetable oil. And these squiggly lines are the long fatty acids, which are the R groups on the acyl triglyceride structure. So imagine that these are being oxidized with ozone. So can I have the next slide? Yeah, so here we go. So here we have oleic acid. It's found in olive oil. And it oxidizes, and it's going to give you what? It's going to give you nonenal, the C9 aldehyde. And we see this using GCMS all the time in indoor air. It's really common. Next slide, please. Now, linoleic acid, it's also found in olive oil or in linseed oil and some other oils. So very common. This produces hexanal on oxidation. And hexanal is one of the most common chemicals found in indoor air today. And it doesn't really have an obvious source. I think this is basically where it comes from, is ozone oxidation of olive oil and other vegetable oils producing this hexanal. But
Now,
the original report from the home that we're studying here contained hexanal.
now, would this only occur when ozone was in a high concentration, like, they're intentionally putting ozone into a home, or could it also occur as a result of ozone from outdoor air getting into a home?
Yeah, that's a great question. It's ambient ozone will do this. So, I worked for a company once. We built ozone meters, and we'd fire up an ozone meter in the building and walk around. It would read 0. You walk outside, and the needle just shoots up. And outdoor ozone is usually pretty high compared to indoor. So the ozone comes inside through the front door or through the ERV or however, and it reacts. Yeah, so the hexanol we see daily in our indoor air samples, it probably comes from ambient ozone. So
Interesting.
yeah,
Very interesting.
excuse me. So go to the next slide. So we had linoleic acid, which is a 1,4-diene. Now it's already reacted once with ozone. It produced hexanal, but it left this aldehyde left attached to the acyl triglyceride unit. So what happens now? Well, there's another alkene here, which can react with another molecule of ozone, and that's going to produce MDA on loss of the oxygen from the ozone ion. So that's a proposal concerning how the MDA can form in indoor air from oxidation of unsaturated fatty acids. Do I have the next slide? Let's see what I have here. Oh yeah, here we go. Okay, so we can conclude, that we definitely detected MDA in indoor air with that heavily ozonized house, and we can detect it by HPLC or IC, and we're still developing methods to get good quantitation there. I can't give you a detection limit on that right now. There's a lot of work we still have to do there.
So in the case study that you were talking about, what was the solution to remove the throw rugs, and did you air it out? Did you heat it?
That's a really good question. Really good question. And tell you what, so that's another way of giving the presentation, is to talk about the solution. And absolutely, the owner used sodium carbonate, and he removed a hardwood floor, which he thought was producing a lot of formaldehyde, and covered it with sodium bicarbonate. So they had half the first floor of the house, 1,000 square feet, covered with sodium bicarbonate. And that made things better. And that makes sense, because the malondialdehyde should react with sodium bicarbonate to give an enolate. It would become a salt. So it would be captured by the sodium bicarbonate on the floor, and then they sweep it up.
Great example of how coordination between the lab and the people in the field can help solve a problem like that.
Yeah. So
Hey,
they're
we've got
back
to
in their
stop.
house. They're back in their house. However, now we also removed a lot of stuff from the house to get rid of the formaldehyde. And I spent a couple of days there with the gas tech sampling tubes for formaldehyde. Have you used those?
Yeah.
No.
They can be useful. We're not selling those, but I'm impressed with that test. You can't measure low concentrations with it, but you can measure higher concentrations. And so what you can do is you can go into the house, you can take an item out, like a valence from the drapes or whatever it is, and you can put that in a big plastic garbage bag in the garage, and then you can let it sit for an hour, let it outgas, and then you can put a gas tech tube into that bag and sample. And you'll, if the object's outgassing, you're gonna get 100 ppb or more formaldehyde, and you can see that with a gas tech tube. So we went through all of their belongings with garbage bags and a big box of gas tech tubes. And we removed a lot of stuff like the bathroom rugs and some valences and some other things. And we were able to get their concentrations down at the time to 20 parts per billion, 25, something like that, which was good for them. And they moved back into the house after the sodium bicarbonate and after all of this, after the gas tech tube testing of their items. A lot of stuff was thrown away.
Whose idea was it to do the sodium bicarbonate? Your idea?
No, that was their idea.
Okay.
And how?
That was
I'm curious.
serendipitous. That was purely luck. And all of this stuff was going on at the same time. So I didn't get to go in and say, hey, let's use sodium bicarbonate to clean this up because I determined this. No, the homeowner actually did that.
Who ended up paying for all this?
The homeowner.
So the restoration, the contractor was not found or did not help with this?
The contractor disappeared.
Okay. Okay.
Yeah, and that made the homeowner angry. And
I'll bet.
they appeared to do pretty good work. I think they just really overdid it with the ozone machine.
Yeah. As
Extremely.
people, they shouldn't be using ozone on mold remediation, but and then, well, let's thank our sponsors. We got to stop for our halftime. We're a little over, but we're going to thank our sponsors. We're going to come back with the second half with Dr. William Chapman. Our association sponsors are AIHA, Healthy Workplaces, A Healthier World, AIHA.org. The Environmental Information Association, EIA's multidisciplinary membership collects, generates, and disseminates information concerning environmental and occupational health hazards in the built environment at EIA-USA.org. The IICRC, a nonprofit standards development and certifying body for the cleaning and restoration industry, IICRC.org. The Restoration Industry Association, the oldest and largest nonprofit professional trade association dedicated to providing leadership and promoting best practices through advocacy, standards, and professional qualifications for the restoration industry at restorationindustry.org. Actionable insights, no more mistakes, no more missed line items in your Xactimate estimates at getinsights.org. Industry sponsors are Particles Plus, feature-rich particle counters and air quality instrumentation. Count on us, particlesplus.com. BioPlanet at byoplanet.com, improving human, animal, and environmental health with electrostatic spray technology and advanced chemistries at byoplanet.com. All right, we're back with Dr. Chapman. We're talking today about chemicals and indoor air quality and odors. Cliff, let me turn it over to you.
Sure. Dr. Chapman, what would your opinion be on the use of Tedlar bags and or canister sampling?
Yeah, that's a really good question. The bags and the tanks, they're used at EPA 215 for the analysis with GCMS typically. And they can be useful for detecting gases. So let's say you want to detect isobutane or butane or vinyl chloride, in an environmental case. Those are used for detecting vinyl chloride in like a landfill environment or in a situation where there's a plume from, trichloroethylene. That's what those are really useful for. The challenges those methods have is, one is your sample size is obviously restricted to the size of the canister, which limits your sensitivity. And also the sample has to be stable, it has to last until it gets to the laboratory. Not all chemicals are. Semi-volatiles are going to stick to the walls of the tank and contaminate it. So that rules out chloridane or a lot of MVOCs and a lot of chemicals. And then chemicals are reactive. People try to measure ETO, ethylene oxide, using those tanks. And this is a frustrating situation because, what goes in the tank is whatever's in the air. So, there's going to be ammonia in the air. There's always ammonia. odor threshold for ammonia is like 50 parts per million. That's a lot of ammonia. You can't smell it. It's a lot of ammonia. And that goes into the tank too with the ethylene oxide. Ammonia just reacts with the ethylene oxide slowly with time. And that reaction rate is dependent on the humidity. So then you take the tank to the laboratory and the ETO is slowly disappearing, being converted to something else, ethylene glycol or aminoethanol or whatever it might be, maybe some polymer. And so the numbers aren't necessarily correct. So, the tanks are good for measuring freons or, PFASs that are volatile, things like that are really stable chemicals. But, we're not using those techniques now. And the bags are similar. Detecting odor chemicals could be very difficult using those bags.
I got a couple text questions here, and some we may not be able to get to, but one was, let me get to this one right
The
here.
tracer gas one, I think.
Yeah. Planning an ASHRAE research project, we need to measure tracer gas concentrations at several locations. How much do these samplers cost? What is the frequency of sampling?
How much do samplers cost?
Yeah.
Well, it depends on what you're measuring. It's anywhere from $65. As you buy 5 more, it'd be 55, up to $150 per sampler, 160.
Okay.
I think he needs to know, ask the guest what they're trying to sample for, Joe. What's the tracer gas they're using?
ASH.
Okay.
Oh,
And I got another one while you're at it. Are any SVOCs, semi-volatiles, useful for tracking off-gassing from wildfire smoke residues?
well, I think so.
Which ones
It's
might
a good question, and I think the most typical chemicals are polycyclic aromatics from those, and so you'd be measuring things like naphthalene or anthracene or pyrene, or ruberine, or one of those big polycyclic aromatics. You can see those using thermal desorption GCMS pretty well. So those would be the SVOCs that we know now would be useful. In the future, I think we're going to have some of these nano particles, the things that are smaller than the PM 2.5s, which are the big polycyclic aromatics. Those are going to be in those gases.
Cliff?
But it's a really interesting question, and that I'm saying because there are a lot of other interesting possibilities, but a lot of work needs to be done there. We have new analytical methods which are more sensitive now. We can see chemicals at lower concentrations in these situations. We have to go look.
Speaking of this new equipment, I would suspect that a number of our listeners are unfamiliar with how a GC mass spec instrument would work. And, if you could provide a simple definition or explanation of how it works, I think they would appreciate it.
Well, sure. So, I could describe how, traditional GCMS works, and then how the newer models are improving sensitivity and specificity an awful lot. So, it's a type of gas chromatograph. So it's the mass spec part's the detector of the gas chromatograph. Now, the traditional gas chromatograph always accepted a liquid sample, and you inject the sample in a liquid into a column, it's called. And the column is like a big distillation column made of metal tubing or glass tubing. And it sits inside an oven, and you slowly ramp the temperature of the oven up in a program in a very well-controlled manner. And the chemicals that you inject boil at some point, and there's gas passing through this tube. We usually use helium gas or hydrogen gas to pass through the chromatography tube. And when the chemicals boil, they of course go through the tube, pass through the tube and into the detector. So the chemicals are basically separated by boiling point, roughly speaking. There are other sources of specificity, but that's the main one, is the boiling point. Now, the detector in the traditional machines was a flame ionization detector, a FID. As I used as a graduate student. There you have a flame, and the chemicals leaving the column will go into the flame. It would burn, and you would detect electrically a change in the conductivity of the flame plasma. That's a traditional FID. That doesn't tell you much about what's being burned. The modern instruments, the mass spec of the GC mass spec, have that flame ionization detector replaced with an actual mass spectrometer. And that's a little bit more complicated, but just in short, the mass spectrometer is inside a big vacuum chamber. It's a vacuum tube. And the sample goes into the mass spectrometer from the column in what's called a leak. So a little bit of this gas goes into the GC. The first thing that it encounters is a filament, or like in an old-fashioned light bulb, red hot filament that causes the molecule to fracture and ionize. It breaks into pieces due to the high temperature. And ions are produced when it's fractured. And this happens in the presence of a high electric field, which accelerates the ions toward the detector. And in the type of mass spectrometer I use, it uses a mass filter in between the ionization source and the detector called a quadrupole. And you just put you oscillate a voltage across metal plates, basically. And only ions of a specific mass are going to be able to pass through this mass filter at a specific frequency of oscillation of the voltage. So you can scan that voltage and then scan the mass you're observing. So in the original mass spec protocols, you would scan the mass you're measuring and look at the detector response. You scan on the order of microseconds, 100 microseconds per scan, something like that. And doing that, you can generate a mass spectrum of the chemical that's coming out of the column and identify the chemical based on this mass spec. The benzene can be at 78. So that's the original mass spec. Today, things are improving a bit on the mass spec side of things, and that our computers, modern computers, are amazing, and they can control this gadget. And one thing you can do today is you can program the mass spectrometer to look for specific molecular weight ions at specific times that should be coming out of the column. So you'd have an authentic sample, say a mold VOC. You put it in your GC, you find how long it takes to go through the column with your specific temperature program. And then at that time, within 10 or 15 seconds, you would signal average on masses that are specific to that mold VOC. And by using a signal averaging method, because people call it single ion monitoring, SIMS, you can get your signal to noise way up. So now you're increasing your sensitivity by hundreds of times. It's amazing what you can see. And that's how we can see, we can see chlorpicrin at parts per trillion, at 10 parts per trillion, way down there. It's very powerful. So that's the newer GC. So one we use is made by Shimatsu, and it's Japanese software, so it's rough, but it really performs. So that's basically the GC and the new detector. Now, there are also new sample introduction methods. You have to put the sample in the front of the column at the low temperature to start the process. And the original method was liquid injection. So to detect benzene, you would take your charcoal sample or whatever it is and expose it. And then you would take that charcoal in the lab, you put it in a vial, and you add 2 mils of a solvent to it. And the solvent would dissolve the benzene. And then you dissolve the benzene, detect the benzene, you detect the benzene in that solvent. And you do that by shooting a small portion of it into the GC, the liquid injection method, using a syringe. And you'd only see 1/1000th of the sample because you're using a milliliter solvent, but you're only injecting a microliter into the instrument. So that was a real sensitivity limitation of the original methods that are used for air testing. This is what we did at Advanced Chemical Sensors for years. Most of those methods are developed by OSHA. So you've heard of OSHA 1010 or OSHA this or OSHA that. Those methods all call for solvent desorption, usually using carbon disulfide of all things. It's the most awful solvent to work with. You shoot a little bit in and you end up losing, your sensitivity. So the newer methods, when we're using, is called thermal desorption. And in this case, what you do is you take the adsorbent from the sampling event and you put it inside a glass tube. And ours is helping place a little glass frit. You put some glass wool in the back to hold it in place. You put that in an instrument, and the instrument will heat that up to 250 or 300 degrees Celsius and vaporize the VOCs. And you blow that using helium gas into a secondary cold trap. We have a cold trap that uses a Peltier cooler. It'll cool it down to -20 degrees C. It captures that. And then we can ramp the temperature of our trap up really fast. And that basically ejects the sample into the column. So now we're analyzing the entire sample, or a large majority of it. So you're increasing your sensitivity by 1,000-fold, and you can start seeing these odor chemicals or whatever they are, irritants that they're in people's homes.
Let's go to the roundup, and we'll come back. And I've got another question from our audience. And Cliff, you may have a final thought. All right. So today's roundup, I want to ask, I've got a text question in here, and I want to kind of modify it a little bit. There are a lot of sensors now, these low-cost sensors that people use for indoor air quality in their homes. So IAQ monitors in their homes, and many of them measure VOCs to one degree or another. Are there any that you found? I don't know how much you deal with these or not, but are there any that you found that can be useful?
Well, so far they're sort of confusing. Yeah, I don't have a lot to say about those. In the previous job, we built gas monitors for professional use. And I can tell you that the big issues that those things have is with specificity. And you don't know what's causing that needle to move unless, you're at work. And, let's say somebody's working in a nitric acid production plant. They have tons of nitrogen dioxide there. Well, then what is setting off the meter? Well, it's nitrogen dioxide, obviously. Or someone has benzene, in a petroleum refinery. Well, then, it might be helpful. But, you're going to have toluene too and xylene. And the sensors can't distinguish between those these days. At least the lower cost ones don't. So the problem with them is with specificity. And you really can't say what you're detecting. So, you have carbon monoxide floating in the detector, probably generating a signal. And carbon monoxide is a bad boy, indoor air bad boy, all right. But a part per million is typical, that's not going to hurt you. Formaldehyde, we need to measure down to 5 to 6 parts per billion. We try to maintain about a 1 part per billion detection limit in the lab here. And the indoor air quality sensors that claim to measure formaldehyde, they're nowhere near that. It's somewhat frightening. People believe that those things work, and I've honestly never seen them work. So
interesting. Cliff?
Though, yeah, you could use PIDs for some purposes. If you know what you're looking for, sure, you can use a PID to detect. It works great.
Cliff?
But you have to know what you're looking for.
Thanks, Joe. I think one of the things that I appreciate the most that you said, Dr. Chapman, was you mentioned that something that Joe and I have been advocating for many years. A lot of research goes on at universities and laboratories and so on and so forth. Mm-hmm. And there generally has been a disconnect between practitioners in the field. Mm-hmm. And sometimes the practitioners don't understand the research, and I think sometimes the research isn't really practical for people to use in the field. And we met You were recommended to me by a CIH that I know and trust, and then I introduced you to a client that we're both working for now and trying to solve her problem. And it's probably the most difficult one I've ever encountered in my life. But in any event, hopefully we'll resolve it. But I think you're absolutely right. We just need this bridge really between research and practice. And
absolutely. We've made big advances in working with that customer. With your patch test on walls with our diffuser samplers inside. I mean, that's really cool. That'll become a standard. That's going to work great. So we have a lot of problems like that in Florida. People come to retire here, and then we have mold. It's the land of mold and mildew and air quality disasters because you're sealing the house to save on energy. And the elderly people have more indoor air problems than everybody else does. They're stay at home more and are just more sensitive. So
before we wrap this up, is there anything we missed that you'd like to add?
Well, no.
A couple other topics we wanted to touch on. We didn't really get a
there's
chance.
all sorts of stuff to talk about. Well, maybe we can just talk another day instead of going up on other topics.
That sounds good to me. Cliff, any final thoughts or questions?
No, Joe, thank you.
All right. This is Radio Joe saying thanks to Dr. William Chapman. Very interesting discussion today on chemical monitoring for IAQ and odors. We'll be back next Friday at noon. I also want to thank my co-host, the Z-Man, Cliff Zlotnick, Grayson Gone Fishing, Fisher at the controls, and most importantly, our audience and our sponsors. We'll be back next Friday at noon with the next episode of IAQ Radio Plus.
For IAQ Radio, I'm Spike Reel saying thanks for listening.